we're going to basically walk through some of the basic parts of two-dimensional motion and free fall. So we'll do a little bit of introduction. I've got a couple of video clips to watch and hopefully get some comments out of. We're going to go over what is free fall, what is little g, how do we describe that sort of stuff. And then we'll go into motion in two dimensions and talk about, well, does the direction you're moving matter? How do we deal with moving in multiple directions at the same time? Then we're going to do some problem solving steps. We're going to talk about what happens if we're not just moving in one direction and then start moving in another, and get into what happens if we're launching at an angle as well. And then if we have time, some practice problems on the end. If you guys have any questions at any time, please feel free to stop me, throw up some questions in the chat, and I'll be glad to do my best to answer them. There. All right, so hopefully this video works and you guys can hear and see what's going on. But this is basically a video from BBC Two. This is Brian Cox. He's a British physicist visiting the world's biggest vacuum chamber. And what he's going to do is he's going to take a feather and he's going to take a bowling ball and we're going to drop them in the vacuum chamber and see what happens. So while I'm getting this queued up, I would love if you guys could take a minute and predict what's going to happen. Are they going to, is the feather going to fall the same as the bowling ball? Is the bowling ball going to beat the feather to the ground? Do they behave exactly the same, whether there's air in the room or not in the room? And how does that work exactly? So let's see if this works.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built out a concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space.
All right, so here's our
experiment. It was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
All right, so first prediction, which one's going to fall fastest? There. So this is no tricks. It's pure air in there. There's nothing going on fun. Which one do you think is going to fall faster? And off we go. And dramatic music.
Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
We dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
60 millitorr fan is 10% loaded. Station 1, go for drive. PCD 30-1, pressure set point 240 psi. Here, go for drop. 9, 9, 8, 7, 6, 5, 4, Amazon, 2, 1.
All right, so here, same thing, bowling ball and feather, but now we're dropping it in a perfect vacuum. Is that going to make a difference? Is that going to change how these things fall? Why don't you guys throw up a comment in the chat and just what you're thinking. Right or wrong, doesn't matter. What do you think is going to happen now if we drop these things in a vacuum? Yeah, so Eli says they're going to fall at the same rate. And let's see if they're right here.
Release.
And there we go. Falling straight down at exactly the same rate. All right, so definitely something we don't see every day in the real world, but this is what would happen if these two objects were falling in a vacuum without any air getting in the way. Okay, this leads us to the wonderful definition of freefall. So freefall is our first topic here, that we have an object that is falling freely. And what do we mean by that? Well, we mean pretty simple. Well, obviously the object's falling. And it doesn't matter what it was doing before it was falling. We could have dropped this. We could have thrown it straight up in the air. We could have thrown it down or thrown it at an angle. It's all the same basic motion here when we're talking about this. But the big point is the only force acting on it, the only thing that's actually accelerating this object is the force of gravity. And as long as we are relatively close to the surface of the Earth, we get to ignore any air resistance in between. That doesn't matter. The air is not going to make a big difference, if any difference, on here. And as long as we're on or near the surface of the Earth, the acceleration of this object is about 10 meters per second squared, and it's a constant value. None of the stuff we're going to be dealing with today gets us far enough away from the surface of the Earth that this becomes untrue. So any falling object, we just talk about being in free fall, and we get to neglect air resistance. We know for a fact the acceleration of the object is 10 meters per second squared, pointing down. Okay. So some math time here. I wonder why stuff doesn't show up. So basically, the stuff we're going to have to do for free fall, vertical motion, is pretty much the same stuff you would have to do in horizontal motion. We're going to be looking for things like how far does the object travel? How fast is it moving? How much time does it take to do X, Y, or Z? The only difference here is that we automatically know the acceleration. We'll never have to calculate it because on Earth, it'll always be 10 meters per second squared. So in this case, the most commonly used equation that I teach in my classes and have seen on tests and stuff like that for free fall is the distance one, the y equals y naught plus v naught t plus 1/2 at squared. This is in your reference tables as x equals ... but we're going to change to y just to make it clear we're going up and down. Okay. And we're going to start off talking just about a dropped object. So this gets a little bit simpler. We simplify that to y equals 1/2 gt squared. The y naught's not really important. We're starting at our 0 point. The v naught is 0 because we're dropping it. And we know the acceleration is g, 10 meters per second squared. For my purposes, I'm not going to put 10 in for g. I'm just going to leave it as 1/2 gt squared. Simply because a lot of the questions we're going to see are going to be derive an expression for, not so much come up with a value for this sort of thing. Okay. Then we can take this equation, this 1/2 gt squared, and solve it for t. And we end up seeing that the time it takes for this object to fall is equal to the square root of 2y, where y was our starting height, or where was our ending height, sorry, the distance it has fallen, over g. And this is super useful because we can see that the time it takes, and as long as we're on Earth, only depends on how far vertically we have fallen. The more you fall vertically, the longer time it takes. And that should be common sense, or kind of a dumb moment, but at the same time, it's important to recognize the math that we're doing supports the basic observations that, yeah, if I drop a ball from higher up, it'll take longer to fall, and stuff like that. In fact, having these shortcuts where any dropped object, I will know time equals square root of 2y over g, saves us the trouble of deriving this every single time. So even though this part isn't on your reference tables, there's no t equals square root of 2y over g, it's not a bad idea to jot it down on a little scratch pad or something like that and say, hey, when we're doing free fall problems, we are dropping an object. The time it takes to fall is equal to the square root of 2y, or 2 delta y, or 2 times the height, however you want to interpret that, all over g. All right, so free fall, basically the same thing as vertical motion. We drop something, it falls down. The only big difference is, as I said before, we always know the acceleration. The acceleration automatically 10 meters per second squared, as long as we get to ignore the air resistance. And as I say that, we need to make sure that when we're doing these questions, we always look to see, is air resistance negligible? Can we ignore it? Because if we can, we're in free fall, a equals 10. If we can't, we're not in a free fall. And we need to realize that our acceleration might be a little bit less or a little bit more, depending on our situation. But we'll cover more of that when we talk about forces and multiple forces acting at the same time. So for right now, as long as we see in the question that we are talking about air resistance being ignored or negligible, or they use the word free fall, we are good to assume that g is 10 meters per second squared no matter what. So that is free fall in a very quick overview. Are there any questions on what we've covered so far? Okay, so nothing yet. If you do have any questions at any time, please just throw them up in the chat. I will do my best to answer them as quickly as you throw them up. So now we're going to do another little video clip, but the question here is now, what happens if we push something sideways at the same time as it's falling? What if we actually go into an arc or a curve in there? So again, I'm going to ask the question here. We saw that in a vacuum, two objects fall at the same rate, regardless of what objects they are. If we do this same sort of thing, but put them sideways and falling, how does that make a difference? Does it make a difference? And what can we do about this? So I'm going to skip ahead a little bit in this video. This is the common shoot and drop. You may have seen this in your physics class. It's a pretty common experiment to do, but essentially, let's see if I find this setup here. There is this wonderful device that is perfectly level so that we don't have to worry about it slanting one way or the other. On one side of it, we have, oh, that wasn't the right click. No, don't do that. On one side of it, we have a device that will just pull a rod out from the ball. So watch, I'll demo that. You can see that this pin goes through. There's a ball that slides over top it. And when that pin gets pulled out, that ball just drops straight down. It has no horizontal velocity at all. It is completely vertical motion. On the other end, you have a little piston that will push a ball off with a horizontal velocity. And these two balls will be at the same height and released at the same exact second. So again, I'm going to pause the video right here. And I want you guys to take a second and throw up a comment in the chat. What do you think is going to happen here? Is the ball that gets a push sideways going to hit the ground first? Are they going to hit the ground at the same time? Does that sideways push make that ball fall slower? What do you think? Is this going to be similar times, way different times, or somewhere in between? Let me know. And the best way I do this with my kids is if you close your eyes. I just want you to hear the sound and see how many things you can hear. Are the sounds hitting the same time? Are they hitting slightly differently? Then I'll play back it through and you can watch this frame by frame. But eyes closed right now. Let's just see if we can hear if there's a difference in the times here. All right. So let's do this again with the actual video going instead of just the audio. Set it up. And these balls go. And they all hit the ground at exactly the same time. There is no difference at all in the amount of time it takes for those balls to hit the ground. The falling one and the pushed one both hit the ground at exactly the same time, no matter what. It doesn't matter how fast you're moving sideways. All that matters is how much you're moving vertically. Okay. So here's an image of what we kind of saw happened here. This one's for a thrown up, but it's exactly the same as a push sideways. The vertical velocity changes. It goes up, 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 then down, down, down. But the horizontal one stays constant. And why is that? Well, in the previous topic, talking about free fall, we saw that the vertical velocity, the vertical stuff, gets accelerated because of gravity. We have a constant acceleration, 10 meters per second squared down. The horizontal one, nothing really happens. It doesn't matter where we are in there. It's a constant value because air resistance would be the only thing that would accelerate us sideways as we're moving through the air. And we are intentionally ignoring air resistance for these questions. So there's no air resistance going on. It just falls straight down or accelerates down because of gravity, and no big difference with a sideways motion on there because there's no acceleration going on. So let's take a look at an example of this that would show up on an AP question. This is from 2016, I believe. It's one of the free response questions that's put out. They talk about two identical spheres released from a device at t equals 0 from the same height h, as shown above. Pretty much exactly the same thing we saw in that video clip. Sphere A has no initial velocity and falls straight down. Sphere B is given a horizontal velocity of magnitude v0 and travels a horizontal distance d before reaching the ground. The spheres both reach the ground at the same time, tf, even though sphere B has covered more distance before landing. And again, those wonderful words there, air resistance is negligible. We get to ignore any effect the air has on there. And so this had multiple parts to it. They had you do some free body diagrams, make some graphs of velocities and stuff like that. But the last part, where most of the points are for this problem, is where I want to focus on right now. And it's in a clear, coherent paragraph length response. This, if you don't know, always shows up on the AP exam. There'll always be at least one of these paragraph response parts where you have to basically make a claim, cite some evidence, and then support it with some reasoning. So in this case, we are supposed to explain why the spheres reach the ground at the same time, even though they are traveling different distances. So let's think about how you would construct that. Again, this is a 13-minute problem. On the actual exam, you'd probably have about 7 to 8 minutes to write this out if you're going with the suggested times. So let me give you guys a few minutes. Let's say, I don't know, 3, 4. Put some thoughts together here. And again, a clear, coherent response should start from basic principles and build up to the therefore ... part. So why don't you guys take a few minutes, think about how you would frame your argument for why these two objects hit the ground at the same time. And then I'll show you a sample student response that AP put out that got full credit for this portion. If this was the actual exam, it'd probably be a good time to start getting some thoughts down and stuff like that. Realizing we just started covering this, and I'm not sure where you guys are in your curriculum. Here's the full-blown response that the AP exam put out, and I modified it slightly to better fit this context. But there's some important parts that we need to say in here. Okay, for example, the first thing we really should say is that reaching the ground first only depends on the vertical stuff. We saw in that video clip that there is no effect of moving sideways on the time it takes to hit the ground. The X direction motion has no impact whatsoever. So all we are looking for is the vertical direction of motion to be the same in this example. So what's the same? When I say what's the same, what things matter about the vertical direction? Well, the first part would be the same height. We saw earlier where we derived the time equation for a dropped object. It depends on the height and it depends on the acceleration. So saying sphere A and sphere B start with the same height, very important. They also have the same initial vertical velocity. You can think about that if sphere A was dropped and sphere B was thrown up in the air, they won't hit the ground at the same time because they have different starting velocities. In this case, though, they both had the same initial velocity, vertically 0. Sphere B had a horizontal velocity that wasn't 0, but it wasn't falling downwards at the beginning, and it wasn't thrown upwards at the beginning. It was just thrown perfectly sideways. So they both had the same vertical velocity, 0 in both these cases. They're both let go at the same time. There's no stagger drop or anything like that that would cause this to be different. And they both have the same acceleration due to gravity, which is 10 meters per second squared, because we get to ignore air resistance. If we didn't get to ignore it, that statement wouldn't exactly be true. So we can find the time, and I'll use throw in the same equation we started with, the y equals y naught. I said this was a very common one to use, and here's a great example of where you can use it. This is the kinematics equation that I would use to find time. And in this case, everything except for time in this equation, we know to be the same for both balls, or both spheres. They both started with the same height. They both ended at the same height. They both started with the same velocity. They both had the same acceleration. The only thing that can change in this equation is t, but there's only one value for t that satisfies this equation, both mathematically and physically, and that must be the same thing for both of these spheres. Therefore, they have to hit the ground at the same time. All right, so here's the sample response here. The AP gave this a 5, and really, this covers all the boxes for this. They started with a claim that it only depends on the vertical direction. There's their explanation. They talk about how they have all the same criteria in there, same height, same initial velocities, same accelerations, same time drop times, dropping in the same instance. They threw in a little math equation proving that t only has, or that you have everything in the equation the same except for t, and therefore t must be the same because there's no other way you can solve the math for it without having those different things. All right, so this one, sample of what you might see on an actual AP exam dealing with this concept. You could also see it as a multiple choice question and say which one's going to hit the ground faster, although typically they tend to go into more detail as to why that is and less memorizing the facts that, oh, same height, same time to fall. But you never know. All right, so that is projectile motion in the two-dimension sense, that I can be moving horizontally and I can be moving vertically at the same time. And I look at the horizontal stuff to do the horizontal stuff, and I look at the vertical stuff to do the vertical stuff. That's about it. The only thing that I would have to worry about there is just being careful when we read through the questions to keep the vertical stuff the same with the vertical and horizontal with horizontal. Don't mix and match. Don't say, oh, I know the acceleration vertically, I'll use it for a horizontal part of this. Okay? And most of the projectile motion questions that we'll run into in exam times and stuff like that will be this sort of a ball rolls off the table, calculate how far away it is. You guys may have done the very common lab experiment, the marble off a table into the cup sort of thing on there. But there's also something else you can do. Okay, we can also launch this thing not just sideways, but what if I actually take a soccer ball or a basketball or a football or pick your favorite sport? There's probably somebody running and jumping or kicking, something that's going both sideways and up and down at the same time. But unlike the previous problem, unlike the rolling a ball off a table, this one starts moving in both directions. Neither one of these two velocities, the horizontal part here or the vertical part here, are zero to begin with, which means we need to add another step into our process. We can't just jump to say, oh, math happens and let's just plug numbers in here. We have to use some trig first. So we've already covered vectors, but just in case you're wondering, this is my S vector, my speed vector, my initial velocity vector. Those are all terms you can see there. And we're going to break it up into components, the horizontal initial velocity and the vertical initial velocity. The vertical part is opposite my angle, so I'm going to use sine in my equation. The horizontal is adjacent to my angle, so I'm going to use cosine. And in the rare event that you know the other two but not S, you can Pythagorean theorem that, or use tangent, or really any other trig stuff that you have covered in there will work. Okay. So a very common question that we would cover with this is, how far away does the object land? Okay. In the AP exam question, they talked about that sphere B landed farther away, but just gave it a letter, said D, said it did land farther away. What if we wanted to calculate how far it goes? Well, for this, really, it's a two-step process. And these steps never really change. This works if you are rolling a ball off a table, and this works if you're shooting something at an angle. Both work just fine there. Okay. Step one is to find out how long the object was in the air for. Usually, not all the time, but probably 90, 95% of the time, you will use the vertical information using this, the y equals y naught equation, your initial vertical velocity, and the acceleration g, 10 meters per second squared down. Once you get that, you can use the horizontal information along with that time to figure out the range, because time is the only quantity, the only thing that we will ever say links the vertical motion to the horizontal motion. They have to occur in the same amount of time. Okay? So let's do some math here, and we're going to derive the equation and the process for doing time of flight. So I would start where I always do for these questions, and my kids at school will say, well, why are we starting with this equation again? Because this is the starting point for projectile motion. Pretty much any projectile motion equation we start with is going to be dealing with y equals y naught plus v naught t plus 1/2 at squared. It's rare that I would start with anything else, especially if you're looking for a time, because you need time to show up in there. Okay. So in this case, we're going to assume that we are starting and landing at the same height. So the starting height here is the same as the landing height here. That's going to simplify our math a little bit and let us do a couple tricks in there. So I'm going to say that I'm ending up on the ground. So my y position is 0. My y naught position is 0 as well. I already started on the ground. So starting and ending both are 0 right there. We have our initial velocity vertically, v naught sine theta. As we saw from the trig equation here, we're looking for the vertical velocity, so that is v naught sine theta. T, because t is there, And then minus 1/2 gt squared. The minus here comes from the fact that there was a difference in directions. And if you guys remember your vectors, if vectors are going in different directions, one of them must be positive, sorry, opposite directions. One of them must be positive, the other one must be negative. So in this case, I'm calling my initial velocity upwards positive, which means the acceleration term has to be negative because it's going down the opposite direction. Yeah. All right, so we take this and I can factor out a t because all the terms have a t there. So divide by a t and then solve for the time term that's left over. And we get this t equals 2v0 sine theta over g. And this will be the time that the ball was in the air for the entire time of flight. Okay. Once we have that time, well, we can go through and calculate the range. So I looked at the vertical information, the y sort of things to find time. Now I'm looking for the range. That's an x direction sort of thing. So I'm going to start with my x equals x naught equation. Again, same exact equation, just x's instead of y's. Very, very, very commonly used equation for this free fall projectile motion sort of stuff. Okay, we're going to simplify it. Well, I'm starting at 0. I'm going to start at my 0, 0 mark. And my acceleration horizontally is 0. If we go back to the pictures of these arrows, these blue arrows horizontally do not change their length at all. Therefore, the acceleration of this horizontal motion for all these blue arrows is 0. They don't change their speed. Okay, so that's 0. So this acceleration term disappears. So we're left with x equals v naught t. We sub in the v naught term from our trig earlier, and we sub in the time term from what we just found. Putting those together, we get x equals v naught squared times 2 sine theta cos theta over g. And realistically, if this was a test question, this is good enough to leave it in. However, your textbook probably will show it as this second term, this v naught squared sine 2 theta over g. What they're doing there is they're using a trig identity, 2 sine x cos x equals sine of 2 theta, and that makes it look nicer. I don't have to worry about doing sines and cosines. I just double the angle and take the trig term with it. Which leads us to some interesting comments about this. In that the angle or the range of the projectile depends on twice the angle. So doing some math, what's the biggest value sine can be? Okay, so sine has its maximum value of 1. It goes from -1 as the smallest to +1 as the biggest. And that happens at a 90-degree angle. So in this case, 2 times theta should be 90, which means this projectile launching and landing at the same height should have its maximum value when the angle is 45 degrees. Okay, now let's test that. I'm going to switch my screen for a second here. And we're going to do a little PhET simulation. So let's see, close that, share the screen. I want to share projectile motion one. So let's see, there it is. Shrink me down again. Okay, so let's see what happens here. We're going to take this wonderful object. It's 0 degrees on the, or 0 meters above the ground. So we are nice and flat. And we're going to try some angles. According to the math we just did, a 45 angle should give us the farthest distance. So let's pick some things. Let's start with 90. I shoot the ball straight up. It comes straight down. It has traveled a grand range of nowhere. It hasn't gone anywhere because sine of 0 is 0, and you end up with 0 meters going on there. Okay? What about if we do a 60-degree angle? Well, I shoot this one, and this goes pretty far. Okay? In this case, our range was 14.4 meters with the given launch speed and other stuff like that. So 14.4 meters, that seems reasonable. Definitely farther than our 90. Okay, What about our 45? Now, if the math was right, this should be our farthest shot yet. And we should never be able to beat it at 0 meters above the ground. So in this case, let's find our thing here. Okay, 16 and a half. We've gone further. That 45-degree angle so far is the winner. Well, let's go down a little bit. Let's say 30-degree angle. Not a 34. How about a 30? Okay, 30, not 31. Let's shoot that one. Let's see what happens here. So that 30-degree or 31-degree angle came in at 14 and a half again. Almost the same exact spot as that 60. And if I got this to actually be a 30, they would land at the same exact spot because, well, trig, the sine of 60 and the sine of 120 give you pretty much the same sine value. They're complementary of each other. So maybe you're saying, well, what if we make it really close to 45, but not quite there? Let's see if we make it 44. Is this going to go any further? Ooh, that's close. But it looks like the 44 and the 45, 16.51, 16.5, let me put it down here, 3301 and 33 more. The 45 is a little bit farther. Can I zoom into there a little more? I can't scroll that way. That's disappointing. So 44 and 45 are close, but that 45 is the biggest value there. Okay. And typically, this sort of question is the kind that you're going to be dealing with for that. The other example you might see, well, let's do the rolling off a table sort of thing here. This is 0-degree angle, shooting perfectly horizontal. This is the other kind of problem that you're going to see where it's just a curve down. And the time it takes for this to hit the ground depends only on the height. So in this case, 1.75 seconds for a 15-meter one. If I shrink that down, this should take much less time and go less far, 1.19 seconds. So the height determines the time it takes to fall when you're shooting sideways. And if you are doing it at the ground, shooting up, the angle determines that. The 90 gives you the greatest time in the air because you're shooting it just straight up in the air. And the 45 gives you the farthest range on there. Okay. And if this was an intro to physics class, this is where I'd leave it and say those two things. But this is AP. And we're going to go a little bit further here as I switch back to my other scenario here, is because we can do both. What if I'm above the ground and I'm shooting it not at a 0-degree angle, but let's say a 30-degree angle? And I shoot this, and it goes and goes and goes and goes. And it lands all the way out here. Is that the farthest it'll go? Does a 45 go farther? Well, short answer is no. Ooh, that's close. But no, the 30-degree angle, so I've got a 45 now, beat, zoom out, shoot, beat the 45. There it is again. The 45 is actually shorter than a 44, which is shorter than a 30. Something changes when I am not shooting or starting and ending at the same height. In fact, this 60-degree one, which if we were on the ground would be out here where the 30-degree one is now way short. And I don't want to know. The 90 is probably still going to be 0. It goes up, it still comes back down, hasn't gone anywhere yet. But the fact that we are at different heights changes the idea with this. So let's do the math for that type of problem. The what if I am starting and ending at the same height or different heights sort of thing. So I'm going to close out PhET again. There's a link to the PhET simulation in the stream resources. If you get a chance, it's a great thing to play around with and just test your thoughts and ideas, or even just to check some homework questions and see if it makes sense and stuff like that. So let me find my slides back up here. There they are. All right, so we're going to continue along here. and talk about what if my starting and ending heights are different? Short answer is it gets a little bit harder to find the time, but our process to get our range equation is still the same. We're still doing a two-step process. Step 1, we are still finding time. And step 2, we are still finding the range. It's still a two-step process. Time comes first. All right, so let's jump in here. So we're going to start off with the same sort of thing. My basic kinematics equation. I'm plugging in the terms that I know about. So I'm going to end up 0 on the ground. Where do I start, though? This time I don't start at 0. I start at a height h, some height above the ground. I have my vertical term to start off with, my v0 sine theta, and I have my acceleration negative because, again, this vertical part is pointing upwards and gravity is pulling downwards. Okay? Now, in this case, what I have my kids do is rearrange this and get it in this form. And the reason I have them get it in this form, this 1/2 gt squared minus v0 sine theta t minus h, so really all I did was multiply everything by -1 in there, is because this is the form they're used to from math. This is t squared. This is t. This is nothing. X squared, x, no x. Ax squared plus bx plus c equals 0. This is a quadratic equation. And a quadratic equation means that I can use the quadratic formula in order to solve this. And that's what we have to do to find our time. This is not something that is easily solved with just algebra. I can't say, oh, well, we can just factor out a t. There's no t in this last term. I can't say, well, I'll just square root everything, because then I can't get my t's together because they're on, one's a square root. That's a pain. Quadratic equation is the way to solve this question. And this is why we learn stuff like that in math, so we can actually do I'm doing a header in soccer and I'm trying to aim it to the bottom of the net. Or I'm shooting a basketball and I want it to go into the hoop, which is higher than my hand released from. This is why we learn that sort of stuff. Okay, so plugging stuff in this case, my A term is 1/2 g, my B term is negative v0 sine theta, and my C term is negative h. So plugging it into the quadratic equation, we get t equals v0 sine theta plus or minus all that wonderful other stuff. This looks messy. This looks not fun. And I hear you if you're saying, I don't want to do all this math. Good news is these questions don't show up very often on AP1 exams. Bad news is they do show up from time to time. We have to know how to do it on there. So I guess kind of just grin and bear it as we get through this here. But this actually looks a whole lot messier than it is. So in this case, we've got 4 1/2. Can simplify to 2. The denominator makes it easier and stuff like that. And we get this t equals v sine theta plus v0 squared sine squared theta plus 2gh over g. And now some of you are noticing that I went from a plus and minus to just a plus. And some of you are saying, well, wait a second. Shouldn't there be 2 answers to this? 2 possible time solutions? I mean, it's a parabola. There's a squared term. I should get one set that works and another set that works. 2 viable points. And the answer is, yeah, you do. But only one of them actually makes sense physically. Because if I look at this parabola, the other end of the parabola is way over here, way over on this negative side. And that would mean I kick a ball forwards, it flies through the air away from me and hits the ground behind me. Or maybe even I kick a ball and it hits the ground before I kicked it. Both those situations seem absurd. I can't have a ball hit the ground before I actually kick it in the air. And unless I'm a really bad golfer, and I have done this, by the way, hitting a ball forward should not result in it going behind you from that. So for those reasons, this is why we get rid of the minus sign here. We're looking for the positive time, the maximum time, which is the time when you land on the ground over here. And once you find the time, the x equals x naught part just comes along for the ride. That part never changes. We just take our distance equation and plug it in and go. And this thing is our answer. And this is where the cool part, at least for me, the cool part comes in, is I can go through and say, okay, kids, what if the height was 0? Well, if the height was 0, this term disappears. This simplifies to v naught sine theta. Adding them together gives me 2v naught sine theta. And this whole equation simplifies to the same exact one that we saw back here. It's the same exact equation as long as the heights are 0. Which is really neat that this equation, this complicated mess of an equation, gives us the same results and more results, more usefulness as our simple one, because this one lets us solve for unevenness and the other one doesn't. Okay. So again, is this something I would ask my kids to memorize? No, not at all. Is this something that I would have my kids take a look at and just say, remember, we could use the quadratic equation to solve problems like this? Yeah, because if it's in lab or maybe on a random test question, they may have to do something like that. It's not super common, but it's also not impossible that you could be asked to do something like that. So the last part, we'll just do a few sample practice questions. Again, these ones are no math. This is just conceptual. Explain answers, that sort of stuff like that. You may get a math question. You may get a conceptual question here, but these are the straightforward ones. So rock A is dropped. Rock B is thrown sideways. Identical rocks. The student draws the following graphs to describe the motion of the rocks using the coordinate system in which the positive vertical direction is up and the positive horizontal direction is away from the cliff. The origin is where they were released from. What's wrong, if anything, with these graphs? If something is wrong, identify it and explain how to correct it. And if the graphs are correct, explain why. So looking at rock A falls straight down. It never ends up farther away from the cliff, which means already I have an issue with rock A's graph up here. This says it has a horizontal velocity, but rock A doesn't move away from the cliff at all. In fact, rock B has a horizontal velocity because it does end up away from the cliff, but this one shows it as flat, having a 0 velocity. That's not right either. So really, these graphs almost look like they're switched. Rock A's horizontal graph should be zeroed, and rock B's should be some positive value. Okay. What about the vertical graphs here for rock A? Rock A starts off with a positive vertical velocity. Nowhere in the question do they mention throwing rock A up in the air, having it stop and then fall back down. They don't throw rock A up and watch it come down. They just drop it. It should just go down. Rock B's looks pretty good. They threw it sideways. So it should start with no velocity vertically and then accelerate at a constant rate. So if I were to have to change these graphs, they'd probably change to be something like this. Rock A's velocity should be 0 vertically or horizontally. Rock B's horizontally should be constant and positive. And rock A's vertical graph should look the same as rock B's vertical graph. They should have the same slope. Both start at 0 and both go negative because they are both falling downwards with no initial vertical velocity. All right. The next one, similar stuff. We're throwing a ball up in the air and down. Let's find the graphs that best match it. So horizontal velocity versus time should be constant. that should be A. Constant, positive, right? Positive is to the left. The ball is going, yep, so positive here. Almost got myself there. If we go the other way, it has to be negative. So they're calling left positive, so positive constant velocity. A works for that one. Horizontal acceleration, nothing. There's no acceleration sideways for that ball. Vertical velocity starts going up, hits the highest point, goes back negative. That looks like I to me. Positive to negative, constant deceleration, constant negative acceleration. That is free fall. That is G. And our acceleration should be B, constant negative graph going in there. Acceleration is always down, negative, and constant. All right. And our last one, more ranking stuff. So which ones go, we're throwing 4 balls up, the same speed, but different directions. How does that change stuff going on? So which one goes in the air for the longest time? Well, that one should be D. I put them all up there. D is thrown straight up in the air. It's going to take the longest to slow down, stop, turn around, and come back down. So D should have the greatest. And then A is thrown more vertically than B, so that should be in the air longer. B is in the air more or vertical than A, so it should go A is the shortest time in the air because you pretty much threw it sideways. B has more, C has more, and D has the most because it's thrown straight up in the air. Horizontal distance, this is the one we're looking for, the 45, in which case it's letter B. B should be the most. D should be the least because it's thrown right up in the air. And I'm assuming that this is a 30 and that's a 60. That might be bad on my part that they're not exactly that way. But this is the only way I can think to rank them here is if the angles are 30 and 60, they will travel the same distance in there. If they're slightly off and I'm really misrepresenting that, then that will not be true. But I can't think of another way to make that claim in there. All right, vertical distance. Well, again, if you're going straight up in the air, you're going to go higher in the air. So A is the smallest because it's not going up in the air very much. And D is the biggest because it's going all the way up in the air and no horizontal in there. And the acceleration of the projectiles, we get to ignore air resistance, which is wonderful. And that means that they all have the same vertical acceleration, which is G. So nothing horizontal, everything vertical. And we go from there. And again, if you want some extra fun, here's the link to the PhET simulation. And you can mess around and shoot various things. You can investigate how mass changes stuff. You can turn on air resistance and see what happens if this was not free fall, but rather real life motion. That works too. But otherwise, yeah, check that out.